I'm so excited. This is the last thing for unit 1 out of our 3 units for the course. Doing this problem, and you will see one like this on the test, so make sure you stick with me here, people, stick with me. Let's do problem 5. This is asking, okay, here we go, asking, that's the phosgene. Actually, I said phosphine earlier, and I said phosgene. No, it's a poisonous gas. That's phosgene, poisonous gas. Not that you needed to know that, but, you know, okay. Given the same reaction concentration, I'm bad at holding this up for you, but you should have your own anyways. Given the same reaction concentrations, the reaction, okay, we got carbon monoxide and chlorine gas makes phosgene. At 250 degrees, it's 1,500 times faster than the same reaction at 150 degrees. Calculate the activation energy. That's the point I want to get to. We're calculating the activation energy. Now, you're relatively smart people, so you at this point have figured out that we haven't used this last equation down here, and we are going to use that equation for this. Now, it wants us to find the activation energy. Okay, so, all right. Oh, that's no good. All right. Nailed it. All right, let's try this marker. I'm running out of markers. Ln K1. That was not a good cursive K. Those my K's are terrible. That's an I. K1 over K2. All right, now equals EA Sports. It's in the game. Can you see that? Yeah, you can. This marker's also dying. All right, now. All right, there's our equation. This equation is used for activation energy problems. Now remember, trust me when I tell you this, I give you problems on the exams like I do in class. This one is asking us to find activation energy. That's what I'm going to have you do in the problem on the exam. So we need to solve this equation for activation energy. Guess which one's activation energy? I don't know, I'm thinking about tossing this one. We'll hang on to it unless we're desperate. Okay, let's go purple. Okay, purple. All right, so it wants us to find the activation energy. It's something about assume the frequency factor. Don't worry about frequency factor. Don't worry about it. You don't need to know what it does. You don't need to know what it does. So I put that in there. After I typed it out, I was like, I'll leave it there, but don't need to know it. Okay, so what we do need to know, though, is this thing here. At 250 degrees, okay, the reaction is 1,500 times faster than the reaction is at 150 degrees Celsius. Now, remember when we first started reaction rates, I gave you this general thing about saying that every 10 degrees Celsius you increase, you double the reaction. That's a kind of a general guideline of what happens. We're going up 100 degrees here. So 100, we're going from 150 to 250. That's going up from 150, it's a difference of 100. So it's going up 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. If we take 2 and put it to the 10th power, let's do quick math and see what we get. 2 times 2, that's 2 2s, it's 4, 8, 16, okay, 32. 6 of them is 64, 128, 256, 512, 1,000 blah, blah, blah. Okay, 1,000 blah, blah, blah. And this is 1,500 times faster. So generally, it's okay. The general rule there, or general guideline, is relatively accurate. I was just pointing that out. Okay, let's get the problem done, because I know you want to get over with and just start studying for your exam, and I appreciate your enthusiasm. We're solving for this. The activation energy. EA Sports, it's in the game. That's your activation energy. All right, we need some things. We need temperatures. That's what T stands for. I didn't even, no, that's the most, I was going to say, I put an I there. What are we doing? T1 times T2, T1 minus T2 are, that might ring a bell for some of you. Chemistry 1, gas laws, R values, gas law constant, yes. Okay, there are 3 of them. Remember, millimeters of mercury, there's one for that. There's one for kilopascals, there's one for that. There was one for atmospheres, there's one for that. Remember that? That's what that is. That's a gas law constant. Okay, those are the rate constants. We weren't given rate constants. Not directly, we weren't. Oh, don't you hate that one? It's not directly given right to you. We were told that the reaction is 1,500 times faster. Okay, 1,500 times faster. What does that mean? Well, in order to get a rate, you have to multiply the concentrations, which are the same. It doesn't say we changed the concentrations. The concentrations at 150 and 250 are the same. So the only thing in the rate law, rate equals K times your concentration. If the concentrations don't change, then the rate's going to change because the rate constant changes. Now, the rate constant, therefore, is directly related to the rate. I'm not writing this down because I'm just trying to explain something, but you don't need to know it. But here's the thing. If it's 1,500 times faster, that must be because the K value is 1,500 times faster. If the concentrations don't change, I will write it down. I know some of you are going, yes, get on with it, please. Okay. There's a rate law. These concentrations are the same at both temperatures. So these don't change the rate. They have nothing to do with it. The only thing that has anything to do with the rate is the K value. And if the rate goes up by 1,500 times, why did it do it? Because the K value went up by 1,500. Okay, it's the only thing to make the rate go up. So if this goes up by 1,500, that's what it said, that went up by 1,500, okay? That's where it came from. I just didn't want to spit it out at you. Some of you are probably unhappy about that, but there's your explanation. So what does that mean? That means I have K values. One is 1,500 times greater than the other one. Put them in. Ln equal Ln 1,500 to 1 equals. It's 1,500 times greater. Well, what if the K value isn't 1,500? What if it's the K value is 3,000? Well, 1,500 times greater would be 3,000 to 2. It doesn't matter what they are. It doesn't matter what the numbers are exactly. It just matters that one is 1,500 times greater than the other one. So I'm going to put in 1,500 for one of them and 1 for the other one. I hope that makes sense. If it doesn't, rewind. Or if it doesn't, some of you just don't care. You just want to move on. So, okay, either way. All right, you're solving for this. I'll call that X. We need R. Wait a minute, you said there are 3 different R values from chemistry 1, which I vaguely remember. Which one do we use? Good question. And that was angsty Billy. That was a good question, Billy. Thank you. See, he's not always angsty. Just got to give him some positive reinforcement sometime. R is going to be based upon, long story short, the kilopascal. There's a reason why, but long story short, kilopascal. That one was the 8.31. So we have to use R is 8.31 in this equation for it to work. So 8.31, that's my R for kilopascals. And I need that to get this to work. Okay, here, temperatures. We're given the 2 temperatures. We're told 1,500 and 250. Oh, so just put those in. No. Why not? Some of you know why. You can never, ever go wrong with Kelvin. You will usually go wrong with Celsius. We got to make those Kelvin absolute temperatures. These have to be Kelvin. Don't forget that, please. Don't forget that on your academic adventure. The last problem on your test will be this problem. Remember to add 273. Add 273. Okay, so the first temperature is 150. Actually, it doesn't make any difference what order you put them in. You want the difference. So if you want the difference, put the larger one first. I mean, that's what you want. You just ignore the negative. You want the difference between the temperatures. So let's see, one is 250 and one is 150. But we have to add 273. So 273 plus 150, that's 373, 423. Okay. And what about 250 plus 273? 250, okay, 250, 350, 450, 523. 100 more, right? 100 more. So 523. Okay, so we're going to subtract those. It doesn't matter what order you put them in, just you ignore the negative because you just want the difference between them. It's irrelevant which way you put them. Down here it doesn't matter. Some of you might say, well, you put the T1 here and the T1 here and T2 here too. Can I put the T1 here and the T2 here? Sure. You're multiplying. It doesn't matter. Just put them in. But make sure you put them in with the Kelvin temperature. So 523 times 423. And there's your setup. Be careful. Don't make a mistake on the algebra. And we got this. We got this. We got this, people. The natural log of 1500 over 1, which is 1500. So I'm going to go in ln 1500. Boom. 7.31 equals x over 8.31. All right. This is 100. But this is a really big number. That's going to be a really big number. 523 times 423 is 221229. Now, you don't have to write all those numbers out. You can round it to 221000 if you want, but I'm going to write them all out. 221229. Boom. That means that divided by that is going to be a really small number. Okay. So let's go ahead and do that. I'm going to get this first. So 100 divided by 221229 is 4.52 times 10 to the negative fourth. 4.52 times 10 to the negative fourth. Now I'm going to go back up top here. So here's what we have. 7.31 equals x over 8.31 multiplied by, I forgot, 4.52 times 10 to the negative fourth. All right. Solving for x. This is being multiplied. In the last equations, we had added this side. We're multiplying, so be careful. This is being divided into. So I need to multiply both sides by 8.31. Multiply this side by 8.31. This goes away. Multiply this side by 8.31. All right. Equals x times 4.52 times 10 to the negative fourth. Now, we're almost done. To get x by itself, divide by 4.52 times 10 to the negative fourth. Divide by 4.52 times 10 to the negative fourth. This goes away. And we're going to get a big number here. This is going to be big. We're dividing by a small number. It means we're going to get a big answer. And that should make sense. Hang on. We'll do over the y. All right, let's do this out. 8.31 times 7.31 divided by 0.0005452. Okay, I get 134,394, or 134,000. I'm going to round it to 400. You can write the whole thing out, doesn't matter. X equals 134,400, and this is going to be in joules. This is energy. Energy is in joules. Okay, so this would be energy. This value here is going to have energy in it. We did a unit analysis. This would have energy in it. So that means we get a lot of joules in order to make this reaction go. Now let's take a look at this. If you look at the reaction, the answer here says 135 kilojoules per mole. Now that is the same answer, except shifting the decimal point over 3 times and making it 130. They rounded to 135. Actually, when I did this out earlier, I rounded 135. It must have been just rounding, but don't worry, it's close enough for government work. So 134.4 kilojoules. Same thing. And that is per mole. It is per mole of this stuff that's being produced. So that would be the activation energy to get this reaction to happen. You would need, if you wanted a mole of this to react, if you wanted a mole of your carbon monoxide and your chlorine gas to react and form this phosgene gas, you would need to put into it that amount of energy, that many kilojoules per mole, which actually isn't very much. It's a big number, it is, because a joule is very small. Remember the joule? It's very small. So this is It looks like a big number, 134 kilojoules. Not so bad, not so bad, because it's such a small number, the joule is for energy. Whew. All right, folks, I'm exhausted, and my thing's almost out of battery, so we gotta stop it. We'll see you at the test, okay? Study up, be prepared. You only get 3 hours, so you got a lot of problems to solve. You gotta know them. Know them.